Hello, hi everyone. My name is Shilpa Elku Ramakrishnaya, and this is my paper for the article that I had chosen. And welcome to my paper review presentation. Today, I'll be covering the topic of efficient diffusion model, specifically a comprehensive survey paper accepted at TMLR in 2025 titled Efficient Diffusion Models, a Survey. The framing question I want to answer is how did generative AI become faster, cheaper, and more practical? Because if you have used stable diffusion, DAL-E, or Mid Journey, you know the results are impressive. But what you might not know is how much engineering work went into making those results possible at a reasonable speed and cost. I'll also share results from a small reproduction experiment I ran using the auto research template. Let's get started and go to the slide 2. Yeah. So before we go ahead, I would like to discuss about the agenda here, and we'll cover 7 topics in total, and what diffusion models actually are, why efficiency became such a critical issue, the three-pillar taxonomy from the survey, then a deep dive into each pillar, algorithm level, system level, and framework level optimization. After that, we'll look at results from my reproduction experiment and finally wrap up with real world applications, challenges, and future directions. So let's go into what are diffusion models next. Let's start with the fundamentals. What is a diffusion model? The core idea is this: a diffusion model learns to reverse a noise corrupting process. During training, you take a clean image, call it like X0, and yeah, clean image here, and you gradually add Gaussian noise to it over t is equal to 1000 time steps. Sorry, by the end the image looks like pure random static. The model is trained to learn how to undo this process. During inference, you start from a random noise, yeah, and run this learned reverse process step by step until a clean image emerges. A good analogy is restoring a blurry photograph, except you are doing it 1000 times in sequence, each step revealing a bit more detail. Looking at the diagram on the left here, so we can say that. And next, looking at the diagram on the right, the forward process goes from a clean image to a pure noise, right? Then for the reverse process, which is what happens when you generate, goes from noise back to a clean image. Each arrow in the diagram here, which we can see here, represents one neural network forward pass through the backbone architecture, which is typically a UNet or a diffusion transformer. And that's the critical bottleneck I want to highlight with this warning box at the bottom. Each reverse steps equals to one full UNet forward pass with 1000 steps. That's 1000 expensive computations just to generate one image. That's the problem the entire survey is trying to solve. Next, let's go to why efficiency matters. Okay, so just how expensive is this? The three stat cards at the top of this PPT tells the story. The traditional DDPM sampling requires 100 to 1000 steps per image. Next, the diffusion models are 10 to 15 times slower than single image pass alternatives like GANs. And running a unit in full pixel space consumes roughly 80% of available GPU memory. The bar chart below compares relative inference cost across different generative model families. You can see that GANs and VAEs are essentially free compared to the DDPM. With 500 steps, users the full bar. Why does this matter? Because these models are no longer just a research experiments. Stable Diffusion processes billions of images per day. Video generation is becoming mainstream. Companies want to run diffusion models on mobile phones, and smaller research teams can't afford 8 GPU A800 clusters just to do inference. Efficiency went from a nice to have to fundamental requirement for practical deployment. So what? So let's go to the next slide. Yeah, let's see the three pillar taxonomy here. The survey organizes all efficiency research into three distinct pillars as we see in this PPT. Let's go with pillar 1, which is algorithm level optimization. This is about changing the model, the math, or the sampling process itself. Think of it as making the recipe smarter. Let's go to the pillar 2, which is system level optimization. This is about extracting more performance from the hardware you already have. GPU kernels, memory layouts, parallelism, making the kitchen more efficient. Let's go to pillar 3, which is framework level optimization. This is about a deployment, which is the libraries, serving infrastructure, and mobile runtime that actually get models in front of users. What I think is most important about this taxonomy is the bottom line you can see here. All three layers must improve together. A faster sampler on slow hardware is only half the answer. A great GPU kernel without an optimized deployment pipeline doesn't help production users. Efficiency is a full stack problem here. Let's go to the next slide, which is algorithm level optimization. Let's go deep into the first layer, algorithm level optimization. This is where the most dramatic improvements have come from. The first, faster samplers. The key insight of DDIM, denoising diffusion implicit models, is to reformulate the reverse process as a non-Markovian deterministic trajectory instead of a stochastic one. This allows you to skip many time steps entirely. The result, you go from 1000 steps down to 2050 with barely any quality loss. DPM solver pushed this further using higher order ODE integration, getting solid quality in just 10 to 20 steps. 10 to 20 steps, yeah. That's at the bottom of this card, 50x to 100x speed up. Let's go to the second one, which is knowledge distillation. The idea here is to teach student compression. You take a large, slow 50-step teacher pipeline and train a small, fast student model to mimic it. Consistency model take this even further. They enforce that every point along the denoising trajectory should map directly to the same clean image. This enables 1 to 4 step generation. The quality cost is only about 3 to 4% on FID score, which is a remarkable trade-off. Let's go to the third one, which is latent diffusion models. The stable diffusion secret, instead of running diffusion in pixel space, which for a 512 cross 512 image means 786,000 dimensions. You first compress the image into a small latent using a VAE encoder. That latent is only 64 cross 64 cross 4, which is equal to 16K dimensions, 49 times smaller. You run diffusion entirely in that compact space, then use a VAE decoder to reconstruct the full resolution image. Memory and compute drop proportionally. This is foundational to every major image generation system today. Fourth, Pruning and quantization. These are classic model compression techniques applied to diffusion. INT8 quantization alone can cut SDXL's unit from 5 GB down to 2.5 GB. INT4 gets you to 1.3 GB. Structure pruning removes entire attention heads. With modern calibration, the quality loss is minimal.